Now I flipped the order because you can see in order to learn file IO, you have no exceptions. He did it the other way around, so I had to do it. But this case, I said, heck with it. I talk about exceptions first. Properly do this. You really should know exceptions in order because it's far more complicated with files in Java than it is with Python, but it's far more powerful. Consequently, you really have to understand exceptions and actually even inheritance. But c'est la vie, we won't talk about inheritance for a while. Okay, quick review. Runtime errors, that's when your program crashes. The runtime errors are basically exceptions in a lot of programs, Java and Python. Ways of handling these error conditions. I said generally, if you can handle these runtime errors, these exceptions with branches, then you should. But it doesn't mean that you always handle branches. There's disadvantages with the exception handling, but exception handling has its place. Now what I'm about to show here is an example of when, yes, you can use branching, but there's some design problems, and it's very much subject to, it's possible you're going to have errors because of those design problems. It's easy to insert logic errors. I screwed up. I reorganized things. Okay, so we have the inventory class. I modified it a little bit from the previous example. Recall the inventory class recap is it's storing the inventory for a store. This is the valid range. And I have a new method rather than just get set. And the example I covered was, why do we need get sets? Why did we make things public? There's a reason why. We can prevent essentially exceeding underflows too low or too high. And in this add one, it's actually a little better than just using a get set. We have an existing stock level, but do we want to change it? We have a temporary value. Say, if we want to add to that amount, we put it in the temporary. We don't change the stock level. And if that temporary is too high, for instance, then it's going to have an error message. And it returns false. It's a status. Were we able to add? No. We can also do the same if it's too low as well, but you get the picture. Now, if it's not too high, and presumably not too low, so we have another branch for that, it's false that it's not too high or not too low. So inventory is going to be in the range from 0 to 100. Then we actually update the stock level. Now it's true that we are able to add the stock. Now, what we have here is branches to be able to check to prevent an exception from occurring, or a runtime, an error from occurring, I should say. Fine. There's a drawback with using the branch approach. Now, even your small programs, it's not. Yeah, even in your static assignment one, it's not unheard of where you have, say, main call one method, another method calls another one. So you have multiple method calls. It's all one class in your assignment one, but later on, these could be one class, one method, another class, another method, third class. And having just these 3 levels is actually, as we see with the exception handling even, that's unrealistically small, but I'm keeping it so I can fit on one screen. Main point is we've got one object's methods calling another, calling another. This is the final one. We're calling class inventories, add inventory. And we have this status that tells the caller is true or false. If it's false, then we're aware that we couldn't add. There was an error. But when we have the multiple level callers, here's the drawback. First, even if it's just one caller, the caller then has to check. It's not syntactically required that you do this check. So there's a potential logic error right there. They don't do a check for that return value. Second problem. As I said, it's not unrealistic to have a whole sequence of calls. Think even in your 231, it's not inconceivable. You have an assignment where function calls this function calls this one calls this one, that long sequence of calls. So if we've got even just this sequence, long sequence of calls, you have many checks, and then each case return, if this is the one that's supposed to handle it, it has to go through all these intermediate ones, checks and returns. Now consider in real life program, even if this is one person, they might screw up part way through the sequence. If it's a real life program, different people working on this one, well, this guy has to be aware of the internal workings. This is going to return true, false to be able to set up this. Well, this guy also has to do this. These are two different people potentially working on the classes that have to be aware of each of these levels. And if someone screws up intermediate values, it's going to screw up the whole chain. And furthermore, okay, fine, we check for the case, but how do we handle it? Do we return false? In this case, it's dead simple. We return false to the original caller, and then they figure out if it's false, then perhaps we try and have a loop here and reprobe again to add the inventory until we get a valid value. But each step, the more levels that we have, the more people we have involved, the more problems we're going to have likely. So with this approach of trying to prevent errors, yes, this is a good thing where we're trying to make it private, make that attribute private. So this is better than the absolute worst case, where we have to have a public method do it, and we prevent it from going in an invalid range. But there's some drawbacks of this approach where we're trying to prevent an error using branches. This is just one case. So I said if you can write branches to prevent the runtime errors, then you should. Two cases where you've encountered where we should do this rather than using exception handling. One case, array bounds. If you exceed the bounds of the exception, you should not handle that exception generally with a try and catch. It should be handled with branching. If you're trying to access, say, a 1D array, and that index is either too low or too high, check with a branch before you actually access the element. Another case where you can envision where we handle it with branches rather than with exception handling is division by zero. You can have a try and catch with division by zero, just like with the array bounds, but you shouldn't. Division by zero, numerator, denominator, top, bottom. Basically check before you perform division. Is the bottom, the denominator, zero? If it is, don't perform division. Stem it off. So it's better to prevent the errors generally if you can. But in this case, this is showing you can, but there's some drawbacks. So this section is just to motivate one reason why we need to use exceptions. Each have their place. So done properly, the syntax is you try and do something that can cause an exception to occur. And then you have a catch block of the corresponding correct type. Now, you saw in the previous one, we had various types of exceptions. This is the type we could have IO exception, another type that we'll get to shortly, IO exception. Right. What does this look like? Round brackets, it looks like a method call. We have essentially, it looks like a parameter to a method or a function. And in some ways it is, and we'll see why we have to do this. Inside the body, we catch the exception. Fine. We'll see why this is necessary in a bit, what benefits it provides. This is a little different from Python. Okay, so an example, reading input from the keyboard, just to illustrate the exception handling model before we get to files, the proper file approach. Input example. Oops. Oh, not simple file input anymore. Week 6. Oops, examples. There we go. Input example, it's a directory. Okay, just I should have kept it as a separate file, but yeah, let me. Okay. So this program is asking for user input. I said that using the scanner class is more cumbersome than getting print and input. The input function with Python. But I also said previous to Oracle implementing the scanner class, the older way was even worse. It was far harder. This was the older way. You needed two classes. Buffered reader, Input stream reader doesn't tell you much, but my names give you an idea. Input stream reader deals with data at a lower level, character by character. This one, as the name implies, takes those characters, lumps them into a string, a higher level. So you're actually dealing with objects. Okay, now they get the input. Now we have system in. So now the keyboard input becomes input to input stream reader, the low-level keyboard input, and it's handling at the character level. The character input now is passed as a parameter to the constructor for buffered reader, which now allows us to read things as a string. All this so far. Now, to get user input, we saw that prompt. Type in an integer right here. And then string input, we can read a line. Now, instead of reading character by character and trying to convert the characters to an integer, we read line, and then we can pass that string to parseInt. And you've seen this one already. It's a static method. It tells us what we type, then it tries to convert it. And if it can convert it, then it says converted to a number. This is the integer value, converted to an integer. Now, where can the exceptions occur? This is the part I'm trying to show you. How first, there's different types of exceptions. You have to list them. This is an input-output exception. When we try and get it, read it, get the user type in stuff. On the off chance there's a keyboard problem. This one you've seen, the person doesn't type in integer. So where's the exception? Read line. This one I can't duplicate for you because this is like a hardware failure. But you still have to include this call with them to try, and you have to have a corresponding input-output catch block. What's happening we call the read line. Why does this have to be in a try block? Buffered reader. This is, you can see the full API. Here's a part of it. Read line. We look at the description. It throws an IO exception. That means somewhere within the body, if it's trying to get the keyboard input and there's a hardware problem or some other problem and it can't, then an input-output exception gets thrown back. Not to here, but it looks for the corresponding catch block, IO exception right here, and that's where it handles it. Now, I can't do this as a demo because that's likely it's from a hardware failure, but the other one I included, I can show you as a demo. The second place where exception can occur, you saw with integer parseInt. If I type in a non-integer value, it passes it to parseInt, it's going to result in a runtime error. Type in an integer. And all this means that we have a runtime error. Exception. I'll explain this in a moment. How did we get all this? When we called parseInt, it called this static method. In this case, it throws a different type of exception, number format. Number format exception, in this case, it's not an integer. The format's not correct. And this could occur if I enter in a floating point value too, because it's not that decimal. It looks at the ASCII code, essentially. The ASCII code's not one of the ones for the digits. So how does this process actually occur? Well, this is where I can illustrate this, why we have these round brackets here. We call this method, this code starts executing. We pass to it the string that we've read in, assuming there's no input-output errors. And I've never had one. I've run this example. If the person did the oopsie, like something like this, what happens within the code? The throws number format exception means that it actually instantiates a number format exception object. And it tosses, that throws part means execution, it tosses this object back to the corresponding try catch block here. I didn't make this point in the first lecture, but now I'm a little bit better here. I was thinking I was driving home. It goes straight to the corresponding catch, even if there are multiple and there are actually multiple methods in between here. When we can debugging messages here, we'll see there's a whole bunch of intervening methods that are being called from here to here after we call this. But now, because we go straight to this one, we don't have that problem of all these intervening ones having to do anything. It basically just bypasses all that and goes straight back to here. Nice. Okay, fine. Now that we're back to here, we've instantiated an object. This is why it looks kind of like a method parameter, because we have this object. This object's now available. This object contains information about what caused that runtime error. So we have code here to deal with it. At the very least, put a print for yourself saying we had a number format exception, so you're aware of it, as well as what type of exception. Now, what can we do built into Java with this class? This is the class. What capabilities, what information can be provided? Well, I have my own generic message. You entered a non-integer value was entered. Then I separate these with these lines here. Get message. What do we get here? The get message doesn't say too much. It said for input string, I typed in my name in this case. In this case, I typed in this. So it says the input string was 12.5. And then you can examine and determine, wait, okay, I have a decimal here. So it has some value. It echoes back what was typed. Because this is an object, we're basically calling a method of the object. It's included in exception objects. This, if we pass it to println, recall if we pass by default a reference to an object, it normally produces something that's not meaningful. But in this case, there is a method that's written automatically that will be called to display something a little more meaningful. It doesn't display, normally you'll see class name @ and then you see the hash code. I briefly mentioned that. In this case, that method indicates a little bit more. So it says what we have here, but also tells us what exception has occurred. Stack trace, what is this? So through the object, we're calling the stack trace method. Recall when we talk about memory types, there's heap. Heap is the part of memory for dynamic memory. So when we have that new keyword, we create a new array, we create a new object. The memory for this dynamic memory is stored in the heap. Another type of memory talked about was the stack. The system stack occurs when we call a function or method. It stores the parameters and local variables in there. It's called stack because we stack it up. Now, with that in mind, the stack trace, recall I talked about debugging messages before reading week. Some debug messages were displaying the state of variables. Another one was essentially what I call the stack trace, showing the method calls. So looking back here, even just look at the actual code so you know I'm not cheating. Input example, the complete one. So I'm calling integer parseInt. Integer parseInt. If I enter non-integer value, it jumps right here. There's no other method calls that I have, but there's other method calls automatically occurring. And we can see them with the stack trace. In this case, it's probably not so useful, but sometimes it can be useful, as I indicated when I talk about debugging. Driver line 39. So it tells me where in my program. This is one advantage of IntelliJ. It tells you a line number, so you have to don't count. That's line 39. This one called integers parseInt method, line 476 in that class, which then called that parseInt method 426. So there's these intermediate calls. And then number formatting. Oh, this looks like it's instantiation, but it's bypassing all these intermediate calls and going straight back to the catch. Regardless of how many we have in this intervening between when we called, what the heck was it? Class integers parseInt, and then the end result, the final ones, it's still going to go back to here. It skips past it. Now, on the note of debugging, some of you at the beginning of reading week, you sent me emails, a few of you did, saying I'm having trouble with assignment number 1. Essentially, it was logic errors. My board isn't displaying properly. What should I do? In worst cases, some of you actually just said, okay, my board's not displaying properly, describe the error, and that's it, not even showing me the code. Imagine an exam question where I said, debug this program, but I don't show you the program. That's in essence what you're asking. Now, in that case, they didn't say anything about actually what they tried to do to debug the program. What should you do in that case when you've got a logic error in your program? Someone laughed in the first morning lecture. Well, essentially, this is why I talked about testing and debugging before reading week, not just because it's in curriculum, because it's a valuable thing. Now, the testing in of itself actually tends to come after you debug the program for major bugs. You're reasonably sure it's working. Before you do the testing of things like JUnit, what do you do if you have those logic errors? This person wasn't ready. These people weren't ready to do the JUnit test potentially. Well, this is where you can use things like debugger that apparently someone in their morning class stuck their hand said it's actually pretty good. That was his opinion. And I take him at his word. One of your classmates said that, so it wasn't me, an experienced person. Use debugger in the way that I described to try and figure out which methods call, where your board, look at the board and look at the state of the board. Use manual debugging tips, the prints, the breakpoints, the other things that I've talked about, the breadcrumbs, the stack traces to figure out what's happening. If after you've done this and still you're stuck, which sometimes happens, that's where you can go for help. But the first thing you should do is, if you've got a logic error, don't just stare at it. Don't just try and run it randomly. Try and actually have these debugging tools to try and find and fix the error on your own. This is the necessary skill that you will have to develop. You can't just rely on someone else. But if you made that extra step, by all means do ask for help. On that note, as I mentioned, CT wasn't available due to an oversight for assignment 1, but I put in a reminder to make sure that assignment 2 and assignment 3 will have those help sessions available. So they're outside the tutorial. They should be when the TAs are available for help. Okay, now I better move on. So now you know why we actually have this. This is a varying information, but what you can also do, there's a little bit at the end of this section where I show, because I have to, how you can write your own exception classes. That involves inheritance. And you can have more customized useful messages. But I don't actually include that because I don't have enough time, and Professor Hudson doesn't include that here. So don't do the following. The term I saw someone, I don't know if it's an official term, but he called this squelching your exceptions. Whether it's an official term, don't do this. Squelching exceptions refers to where you have a catch block. You have to have a catch block for syntax. This will prevent the syntax errors, but this is an awful thing. Why is it awful? You're asking for trouble sooner or later if you do something like this. Thoughts why? And okay, well, think about what happens if we have an exception. A number format exception, person types in an int. Execution transfers here, no visible output. We don't even alert the programmer that there's a problem, let alone recover from the problem. So you have potentially a logic error occurring or a runtime error, and you're not even aware of it, so you're not going to do anything about it. At least put a print saying number format exception occurred. I put this here because it seems like it's a little talking down people, but first time I talked to 33 was 8 o'clock in Earth Sciences. And I remember I would show how not to, and then students would ask things at the end of class, at least they asked the end of class. 8 o'clock, they're probably sleepy. Then they woke up the end of class saying, why would we want to do something like this? This is bad. I said, no. This is an example of how not to do it. So I said, heck with it. I put it in notes because people might miss when you're hearing me saying it, but now they see in the notes, they won't see, oh, Tam put it in notes, so we're supposed to do it that way. No, I also have to teach you approaches, bad approaches, and not to do these bad approaches and why. Finally, the finally is guaranteed to execute even if you do stupid things to try and bypass it. I'm about to do something where I say, try not to do it, do this at home. I might not have time to cover this. Now, you should know from Python, they have the equivalent of finally, whether or not an exception occurs. The exception did occur, the finally block executes. If an exception doesn't occur, the finally block still executes. Now you might ask, why not just exclude this and just put a statement right here without a finally? Because whether or not we have an exception occur, it's going to continue after. If there's no exception, then it skips the catch, comes here. If we have an exception, then we come here. But I have that finally example, the do not try it at home, just to show that even if you do extraordinary measures, if you do those extraordinary measures, this will get bypassed. So with the finally block, it will not get bypassed. So this example, what I've done is I've taken all the other code. It's the same execution. So all the other code that I have, where the heck is it? It's easier to show the whole thing. So all the code that was in main and in driver, I've moved it off to another class, so I have a method call. So I have another class here. So all this is moved to a different class. And I'm going to have a return here just to force, just to prove that finally always, that will always execute. Okay. So this is empty, but I have a new class here, try catch finally example. So all the code that was previously in the driver, so here's the driver. So we have this try, enter an integer, and so on. Now it's moved over here to this method in the try catch finally example. Why did I do that? Because I'm going to try and bypass the finally. You should not do this, but I'm doing it for learning purposes. So here's the code inside the try catch finally example, enter an integer. I have a return here. So if no exception occurs, we're going to try and return back the caller, which is main. I'm forcing it to try and bypass the finally. Furthermore, inside, if an exception occurs, I have another one. Again, I say don't do this with actual code because this is asking for trouble normally, but this is for learning purposes. If we have a either exception, we try and have a return. Now, if the finally executes, we'll always see this message. This code will always execute. Do we see it? Yes, we will. So if we have no exception occur, do we see that this code will always execute? There it is. Even though no exception occurs, there's a return. This is trying to bypass that finally block, and we can't. What if an exception occurs? This one I can't duplicate, this one I can duplicate. The enter a non-integer value. We have all the other previous information proved again. It always appears. Now, with this in mind, don't try and bypass the system, but I'm trying to say, why do you need a finally? It always executes. If we didn't have it, we just had statements here outside of finally, the returns would take over. However, the newer Java compiler, it prevents you from doing such. It's able to detect the returns in the finally. Because I tried this just for the heck of it, compiling it, you should usually do a fresh compile. And this wildcard is going to compile everything that ends in .java. In other words, compile all my code, but it's going to die out. Oh, wait, sorry, Javac. It dies out and it tells me I'm trying to do something stupid. The returns, it doesn't clearly indicate it, but those returns is the problem. How did I actually get this code? Because in an older version of the Java language with a different compiler, I actually compile, oh no, yeah, there it is. See, time date stamp is from 2020. 5 years ago, 4 years ago, it allowed this, that version of Java. And there you go, it produced the class file, but it can't produce a new one. But the learning lesson is just this, guaranteed to execute, but don't do this, even if you have a compiler that will let you do it. Okay, how are we doing for time? I got to where the other lecture is, and I think we're close to time. Oh, we're close to time. Okay, what's coming up next? Okay, I'll just briefly introduce it. I won't have time to trace this. What if we have this method and it's calling something where an exception can occur, but in method one, the guy writing this class doesn't know how to handle it. What can we do here? And there's different ways of handling this. So this is introducing the other. So where I left off last day was here. People coming in. And just beyond this, introduced somebody had the other class. Delegating exceptions. So previous to this, you actually, when you called a method where an exception could be thrown, you had to include that method call in the try block, and you had to have a catch block of the appropriate type. Now, what if the caller actually it's not appropriate to handle it? Here's an example of this is actually a layout of the calls that I have for this next one, where the caller can't handle it. Now, this is called a sequence diagram, that an official one that's part of UML, Unified Modeling Language. We'll talk about UML for class diagrams. This isn't necessary unless we cover it later, but it shows the calls. Here's the class name, the method, and it shows a sequence of calls. This is one class. This is another one where I move some code over here. Now in this code, we're going to call these two methods you've seen previously where exceptions can occur. Previously, when I called these ones, we actually had to include the calls within a try block. But now the calls are here. What if this caller can't handle it? Why would that occur? There's two reasons. One reason is the person writing this code doesn't know how to handle it. It could be there's one person writing this, another person writing this. This dude doesn't know how to handle it. Another reason why we don't want this caller of these two methods to actually handle it is I could be the author of both of these, but in terms of behaviors, it doesn't make sense to have a method here. The behavior of handling it belongs here. So I'm actually going to put the behavior over here, the handle, the catch block over here. This one does the call. How do we do it? That's what I'm referring to here. So driver calls method of try catch finally example. It's just a filler class. I move code over here. And we see the same sequence. Buffer greeter read line. An IO exception can occur, but that's a hardware failure. And I can't duplicate that. Well, not without wrecking some hardware. So we don't have an exception occur. The enter in a 10, fine. No exception occurs. Then we recall we convert to an integer using parseInt. So we call the parseInt. This is an integer. What happens if no exception occurs? Then we go back to caller, go back here. What I have here is a loop. This loop is essentially allows you to recover from an error. If there are no exceptions, fine, we break out a loop. If there's any exceptions, then we'll recover from the error and continually ask the person for a valid value, which is the next one. So we have the same sequence of calls, but now we're going to have an exception. They enter in something that can't be converted to an integer. No IO exception. But then when we pass it to parseInt, we can't convert to an integer because that's not the ASCII value of an integer. So an exception is thrown. This dude can't handle it. This is another advantage of exception handling, where this is the one that's doing the call, but it's able to skip through all these intermediate ones and go to where it should be handled. We don't have to have any ifs. Over here, if we enter in something that is not an integer, well then inside a loop, we re-request it again, and we have the opportunity. We enter in something not an integer, it continues forever. How I've set this up. So we have main. Main instantiates a try catch example. We have that code moved over here. The input OK is a flag. We assume that by default, unless proven otherwise, that the person entered in their input correctly. And there's the aforementioned loop. Well, it's true that the input is not OK, we loop, but by default, we assume it's OK. And now, whoops, we instantiate an example of the try catch example. I just moved the code over here again to show, well, this class doesn't handle the exception. How do we do it? Well, we're going to call the method. And if we call it, go through that sequence right here. So this is going to call readline. This is going to call parseInt. If there's no exception, then we return back the caller. And it says we break out a loop. Right here, that means no exception occurred. These ones don't kick in. So we set the flag to true. The flag is true. We'll break out a loop. And we need to set it to true because if we previously set it to false, well, it's still going to stay false and it's going to continue. If, say, the person entered in something that was invalid here, that flag would be then set to false, and we're back here. It'd be set here. It's invalid. Then when the person enters in something, it's okay. That's why we need to set it back to true. Okay, fine. Let's look at this method, example method. Notice that the call to example method is include a try block. Recall that what if the caller of we don't call it parse it over here. Notice that. But what if the caller parse it can't handle it? We delegate it back to pass the buck to the caller of this one. Now this method throws the exception. This handles the syntax requirements where we call, what is it, this and this. Normally those ones have to be enclosed in a try block. We don't, because now we just say the caller of this method will throw these exceptions if these ones return an exception back. And we return back from method, which is here. Now method throws these exceptions, so it has to be in a try block, and then we go to the appropriate catch block. So we passed the buck previously. And again, we might do this, not handle the exception here, because again, the person writing this class doesn't know how to handle it properly. So we delegate to the dude who writes the class that knows how to handle it. Or it could be someone knows this, but it's not appropriate to include the code for handling it here. Okay, so I have two examples in this directory of delegating. Let's go back now. The delegating is right here. It recovers from the exceptions, and that's driver.java. Delegating exceptions. So I have driver and driver too. They're very close, so I didn't distinguish. So I enter in a non-integer value, it recovers. It's still in that main loop. Non-integer recovers. And it's going to keep doing this forever until I enter in something that's all an integer. And it breaks out of that loop. Fine, then I have driver 2. Driver 2 shows the other way, where what if main can't handle it? If the very start of the program can't handle it, then that method throws an exception. Now, it's calling that example method which throws an exception. Recall, you either have to have this in a try block, or this method throws an exception. But it's still not useless, because at least it flags to this one, passes it back to the caller main, which is Java, the Java interpreter, which is the runtime environment that runs your program. It runs as a virtual machine. At least it'll flag back to the person running program that an exception occurred. Driver, oops, that should be driver 2 actually. Driver 2. So if we enter an integer, no problem. It returns the virtual machine ends, Java ends. But if there's an exception, then it still flags it back. Now, there's possibly what might also occur is if we have this program, like driver 2, called by another program, which is unheard of. When I was a student, I was employed at a software engineering project, PROS1. It was a big one. We had multiple people. And it was complicated where our code, the Java code, was called by another PROS project, research project, so they're collaborating. And I think it was C or C++. I'm not sure this would work, but a possibility is if the other person's code, being Java, if it was a Java program, another Java program calling this one, it passes it back potentially if that Java program could scoop up that exception, where it's more appropriate for that engineering process program to handle it. If it, I'm not dead certain you can actually communicate program to program this way, but even if you can, at least it's flagged down. You fulfill syntax requirements here. Okay. Exception hierarchy. I include this screen grab Professor Hudson's notes because I put it at your fingertips. It's an open book, but just so you have this hierarchy, he might ask you something about the hierarchy. Errors, he says for the VM virtual machine, Java is the Java interpreter, which is the Java virtual machine. It's the one that actually deals with, well, what if you don't have enough RAM? Or you're running a program that's trying to load in a class. But over here, this basically shows the hierarchy in terms of parent and child. I'd actually exclude this. This isn't a class here, but it's a library, a package that includes, I have mentioned the object. It's the parent of all classes in Java. Everybody else is an object. The one that inherits from it, you have learned the concept of inheritance. Yeah, you have learned OO and the theory of inheritance. It was in Professor Zal's 231 required notes, concepts. This one is a child of this one. So that's how this works. And as Professor Hudson's quiz might ask you about the hierarchy on the off chance, you have it at your fingertips here. Now, let's see, exceptions, runtime exceptions. What we have is errors. Errors is the throwable type is, you saw where some methods throw an exception where you can pass it back to the caller. Any class that is a child of throwable has that ability to pass it back to the caller. You can throw instances of that class. The errors are ones that are runtime errors that you shouldn't handle. Exceptions are ones that you should handle. The term for this is called a checked exception, where you have the try catch block. These are unchecked. So the checked exceptions include IO. The errors, the child of the errors, include things like array bounds, where you handle it with a branch. More of the hierarchy shows so the exception types, and then you get the specific ones. This is including Java's, but I wouldn't include all these. The class not found, I try to simplify it, and I do later. The more specific, the child of IL exceptions are more specific versions. Input, output, when you're writing, reading from a file, there's some problem. That's generic classification. But you can have more specific ones. When you're reading Rainford problem, the first problem can occur as you're trying to open it. And there it is. If you're trying to open it and we can't find that file, it is an IL exception because you're communicating to disk, but it's a more specific one. So we have that hierarchy over here. And then the runtime exceptions, these are ones that, these are ones also that you shouldn't catch over here, where we've got arithmetic division by 0. These are the ones, the runtime ones that we shouldn't catch. Hierarchy doesn't communicate it. The part that he shows communicate the ones that we should catch versus not catch. This is the key part because you will need to know this when you have file IO, or you should, even if it's not listed in the requirements for A2, you should be more specific in the type of error that occurred. So for instance, just saying IO exception user doesn't all useful. It could be that the file name was wrong, it doesn't exist, they typed it in wrong, or maybe they're reading past the end of file. So you should be specific in terms of the exception. The only way you can be specific is essentially to have catch blocks for each one for the ones that are relevant. Some of the ones are relevant, end of file if you tried to read past the end of file. File not found. So these ones are specific instances of this. Now the part that I'm going to get to is over here, because when I just say that an end of file exception is an IO exception, you can substitute one for the other, a portion of class misses it. So I use a real life example just to show the substitution in terms of inheritance. If we had a person, a concept of person or a class, they have certain capabilities. A nurse is also a person, but it's a more specific type of person. A nurse is a person that has specific skills in training, nursing skills like bedside, how to do a bed bath properly, potentially how to, courses like vaccinations. They're supposed to know to monitor side effects, for instance. They have skills that a person doesn't have, but they're still a person. Auto mechanic has those skills. But we can substitute in a nurse when we need a person. Example. If, say, an obvious example is if, say, we need a blood donation, there's different blood types. Say we have an emergency and we need someone with old type blood to donate to this poor person who's bleeding. Well, a person is needed. A nurse can donate if that person has O positive blood because they are a person. A mechanic can do it. So we can substitute, if we need a person, a generic concept person, we can substitute these child classes for a person because they're still that person. In a similar fashion now, an end of file exception is a form, a more specific form of an IO exception. You're checking for the case where we read past the end of file. If we need one of these, just like over here, we can substitute the child for the parent, the lower for the upper. Now you need to know this when you're catching the exceptions. The order is important. Catch the more specific cases before you catch the general ones. And you've seen this concept before. I knew it would come up in an exception, so I brought this up. It also is important for branches. So this is a review. If you reverse the order, this is a more general one. Greater than 100 includes this. These are more specific. So you see specific versus general. So If we reverse the order and we include the general one, well, if it's say 123, it's going to be caught here, and this one will never execute. But if we flip it, look at the more specific one, 1, 2, 3, this is the only one that applies. So now this body will execute. In a similar fashion, we reverse the order. Now again, for your reference, here's the hierarchy. The incorrect approach is if we put the IO exception first, because an IO exception, or sorry, an end of file exception is a more specific form of an IO exception. We can substitute this for this. We have a call. Say the call we're trying to, which one is it? End of file. Where we've opened the file and we're reading line by line. Suppose we're reading and during the read of a line, we didn't check for the end of file properly. We read past the end. So we call that method, it returns the corresponding, and it goes catch block. But with the catch block, it goes in order. So it starts at the first one. We read past the end of file, so an end of file exception is then past the catch block. It's looking for an IO exception. It gets an end of file exception. So it'll be flagged here, and this one will never execute. We want less, but we get more. We want a person with O blood type. We get a nurse with O blood type. We'll take it. This is not a syntax error. This would be a logic error. Test it out yourself. Take my code so you don't have to retype it. And then just screw it up, essentially. You don't check for the end of file. Say we have one line, and then we read twice from the file. So the second time we read, we're at the end of file. Order it this way, you put different prints. You'll see that this one, even when we read past the end of file, well, the one that executes, this one will never execute. We put different prints here. On the other hand, reorder it this way. If we have the exception, we read past the end of file, it looks at this one. Ta-da! It'll flag in this one because it checks it first. So we had the more specific before the general. This is the general before more specific, just like this. This is the more general before the more specific. However, if we get an IO exception, it'll still be okay. Suppose we open the file doesn't exist. We get an IO exception, we want an end of file exception. So we want this, we get this. We can't substitute a person for a nurse. We can't substitute a person, can't substitute a person for a nurse here. We need someone to administer first aid. So then we look at the next catch block. It then goes in the corresponding catch block. So whether we get, in this case, if we get an EOF exception, it's going to be here. If we get an IO exception, it's going to skip this, and it's going to come down here. Important thing. This basically is an invisible logic error. Especially if you combine it with squelching exceptions, you'll never be aware. And if we actually have to have code to handle the end of file exception, you'll never be aware of this. In fact, your code could be just invisibly reading past the end of file. And then you've got some problems. The stuff you read from files all munged up and you have a logic error. Participants, I'd see if there's any questions. Okay, over here, inheritance. Hate this, but I'm careful. Again, he's very specific in the quizzes. So if he has something in his notes, I have heard him say it's in the notes, therefore it can be quizzed. Consequently, I'm careful to look through his notes and see what concepts are introduced. In the exceptions, he introduces inheritance, and he doesn't do it just generally, but he actually has code. We haven't gotten into inheritance yet. So he actually has a more specific form of inheritance. How much details he expects, I'm not sure. So I have to at least talk a little bit about this, because what happens when one class inherits from another? And you might want to do this first. Why would you want to do this? Well, the existing exception classes don't handle the case that you're looking for, the more specific one, or it doesn't do it the way you want to. So you want to create a more specific class. What's the basic effects of inheritance? So I'll show you we will get to inheritance later officially, but because he jumps ahead, I have to jump ahead, or at least I should, to do this properly, so you understand this. I have class person. It has two attributes, age and name. Fine. We have a constructor. Based on the parameters, we set the age and name. I could check for validity, but I'm trying to keep it small and simple. That's not the learning objective. We also have a display method. that basically displays the name and age. Fine. They're both public. Public means that anyone can call these. But when we have inheritance, something that's a child of person, not only can we call it, but these ones are actually included in its class definition by default. We don't have to actually write a display method to access this display code, automatically included. Which is what we have here. Child of person, just to clearly indicate that it's a child of a class of class person. This is the syntax for creating a child class. Now, we have a constructor here. It takes an integer and a string. The keyword super, when you're in a constructor for a class and we use super, that means we're calling the superclass's constructor with the same type of arguments. This one takes an int and a string, so we call the one that takes an int and a string. If we had variations where we had overloading, then that's where we could call different overloaded constructors, but I'm keeping it simple now. So automatically, this is going to call a constructor, pass this integer, this string to its parent class, which is over here. And as you saw with the parent class, it'll set those the age and the name attribute properly. It also indirectly gets access to these ones. The child class can't directly access through the dot operator. It can't say age is equal to something because it's private. Private means you can only access it here. But indirectly, we can access age because if we call a method inside one of the child classes, then indirectly we change it. And that's by calling superclasses, the superclass then changes it. Fine. We also have access to the display as if it was included in here. And in fact, because it's included somewhere else, we don't want to define it here. If we want the display of child of person to do the same thing here, just display this, we don't want to write it. We don't need to, nor do we want to write it. To prove this, quick example, I create a person object, age, name. We call display, we get what we expect. That's that simple review. But when we create a child object, age and name, we call display, it worked properly because it sets that age attribute this, name attribute this, and it's calling display. It doesn't have display in child of person, but but it automatically, we don't have to say it's going to call it. Because it extends person, it'll call this one as if it was defined here. So that's very basic introduction to how inheritance works. So back to this, if you write, you can do this. He has this in an example. A child of one of the existing exception classes, then your child class will get all the abilities of the parent, such as the throw capability. And those debugging messages that I showed, by default, where the heck? Here, we don't have to write a stack trace method because it's actually inherited. That's the effect of a new class inheriting from the exception class. More on inheritance later, but again, because he did it, I didn't. He opened up that can of worms. Okay. Okay. File input and output. We just had simple file input with the scanner example in class file. Now, class scanner isn't the typical way in Java that people will perform file input. But the advantage of scanner, one quick one is, because it's a typical way for getting text keyboard input, the methods are familiar. There's some disadvantage of scanner. That was the advantage. The more commonly used method for file input uses file reader and buffered reader. Similar to file and scanner, these ones perform different tasks at a different level. This is the physical file where it's in binary. Every file is in binary. If it's a text file, then the file reader is going to, we have a review. Files are in binary. They're classified in two main categories, either text or non-text. Text basically is where every 8 bits corresponds to an ASCII code. Non-text is anything else a file that is not a text file. So we might have 24 bits become a pixel for a color, or it could be a Word document, which is stored in binary form. That was quick review. So if it's a text file, we'll grab every 8 bits and we lump them together. 8 bits are a byte, and as output, it'll figure out the ASCII characters. If it's not valid, then we're going to get gibberish. Well, at this low level, individual characters, it might be hard to manipulate because then to be able to get a line, you have to do some operations to be able to concatenate them together. That's where we use another helper class that works with the file reader. This one is the one that makes a connection, opens file. This one does not, but this one takes the character stream, output of file reader, and then connects them together. Every line that we read from a file, it connects them together and makes a string. In reverse, writing to a file, we have our program. Our program includes the primitives, the simple atomic types like integers, strings, objects, well, actually references to object, higher level representations. We can pass these and input the print writer. So these are the higher level variables. And print writer can produce as output the character string. So the string, I use that example because it's easier to visualize, is broken down into characters. That becomes input to file writer. These two collaborate. The file writer is the one that actually opens the file for writing and actually does the write. But this one doesn't do the writing, but it can process the higher level representations to a lower level. File writer then converts it from this level, because it has to be in binary, from this, the ASCII code and decimal, to binary, and then writes that to a file. Now, before I get into the code, this is actually an important issue because if you don't understand buffering as a user, you don't understand it as a programmer, you run into problems. As a user, when you have input from the computer, right now input is my mouse, input is me typing in the keyboard. Right now the focus is not on PowerPoint, somewhere else, so it's being stored somewhere. If the computer is busy, sometimes it's really busy, it can't even process simple input like mouse. So if I'm moving it around all over a place and the computer is busy like this, then we're not going to see it draw over. It's just going to sit here. And then when it's not so busy, what happens? It jumps all over the place very quickly. Well, my mouse movements are stored in a buffer so that they're available when the computer is not so busy. It pulls out a buffer and then it processes the mouse movement. That's what I'm going to do here. And you can have the same thing with keyboard input. That's why sometimes when you're typing in stuff, nothing appears on screen, even though I might be, this is the current focus, nothing, now something appears, but if it's busy, nothing appears, what I'm typing gets stored in a buffer. Well, output is also buffered, file output is buffered. When you write to a file, let's look at this diagram. It doesn't directly write to a file, but there's an intermediate buffer. A buffer is a part of memory. It buffers for the same reasons that I described. If the computer is busy. If it's busy and we don't have a buffer, it can't write to the file. What's being written to, attempted to be written to from our program, will be lost because it's not stored and we can't retrieve it and the computer's not busy. So it writes it to a buffer. Theoretically, it's supposed to, if we don't do anything else, when the program ends, it actually takes what's in the buffer and writes it to file. In practice, unless you tell it to in some form, it never does. You could get empty files. Maybe if you write a lot, it'll write some of it, but in practice, I've never had it written. So what you have to do is clear out that buffer. That's called flushing. In fact, that's the methods, that's the actual term. If you close the file properly with a closed method, then it takes what's in the buffer and then flushes it or writes it here. And it does other things. If you open a file for writing, it locks the file so that no other processes can access it. And I suspect that's what's happened with Zoom while it was crashing or freezing. I had it open with another user account. I was making a video to do the JavaDoc explanation, but it was still writing the video. Then I opened up Zoom here, it was still writing. The two processes, the one that I have with this work account was waiting for the other one to finish. So I finally went to my other account, just logged out, so it killed off all, even though I quit out of Zoom, I logged back in to my other account, the processes were still hogging that resource, I presume. Good lesson for today. So I went back over, logged in here. A few times you guys kept getting kicked out of Zoom because the meeting ended. Then I logged back into my other account. I finally said, heck of it, let's kill off all those processes. And I just logged right out. It freed up the processes that weren't locked anymore. Then I was finally able to start up Zoom without freezing it up because those processes were locked in Zoom And from this account, my work account, couldn't access it. A good example of locking. So when you close a file, it not only flushes the buffer of writes, but in that case, when you open a file for writing, it locks it so someone else can't access it until that other process is trying to access it, until that lock is freed. Another approach of getting the buffer to write, say you're writing a lot of stuff and you want to periodically have it written. There's actual flush command called closing the file. We'll talk about that. But this is very important. If we have file writing and we don't actually tell it either to close that file, if we don't close that file explicitly or we don't flush that buffer, you'll see an empty file. I've had that logic error happen to me a few times when I was a student. All my code was, the rest of the program was doing complicated stuff, and even my file output was right. The problem is I forgot that one stupid statement to close the file. And I was looking at this code where the problem is I just missed file close. Occasionally I do as a prof, but I catch it pretty quickly. Okay. And just to look at the API, the flush, it writes basically what's in the buffer. So no bones about it. When you call flush, at that point, what's in the buffer writes the file. They're a little more ambiguous, unfortunately. They should be more explicit, my critique of this. Close, it frees up resources. And they should say, in my opinion, say frees up resources at the very least, including freeing out the buffer. The buffer is a resource. So it implies that in practice, I found that it does do this. Okay, now the program for writing. We use these classes, so these are the four, the writer classes, the reader classes. What I'm going to do to get input is, I get it from the user line at a time. That line is going to be an array element. And I use the scanner to read the input. The paragraph is the lines. So with this program, it's file IO. Okay, so I have a data.txt already. Oops. And I had previously what I wrote to it, so let's blow it away. Run the program, and then I'll get to the trace, show you what's happening. Okay. Command line. So now what's prompting me is enter line. I'll enter in slightly unique stuff, so you can see. And it hasn't created a file yet because I'm basically just in a loop where it's getting the input. Each one of these will be an array element. I can show that code now, right here. No file IO because there's no try and catch. Inside this loop, max, there's going to be 4 array elements. Max is set to 4. Enter line of text, so it's going to be stored in a string. Line is a string. Paragraph is an array of strings. And in this loop, basically, each array element, index 0, what I just entered. So that's index 0, that's index 1, index 2. And it's still in this loop. I have to hit enter before that last one gets registered. Oops, is this frozen? Something's a little wonky. Well, maybe command. Oh, okay, yeah, I had the focus had to be right there. So now we saw some output. What happened? Now I get data.text created. And see what I had here. Fine. Let me blow this away again. I haven't showed the file IO yet, but I will. I'm going to modify this a little bit. This is where I close the file. File reader close. File this again. This is the only one I changed. the oh, do I have a flush here? Oh, this is the wrong one. I had to close. Let's see, where's the writing? Oh, this is the one I forgot. This is the actual writing. I commented out the wrong one in the fool. So what I wanted to do was, this is the key one where it writes to file. See, it actually wrote it to file. I was a little puzzled at first, but I didn't comment out the writing, the file writer's closing. Do this again. So I don't actually close the file. And let me throw this one away again. It will create it. Line of text. Put something different. Empty file. There we go. So I didn't, all I commented out was this close, this, where the heck is it? Write paragraph to file, this close. I compiled it, data.txt, it's empty. This is precisely what I was referring to. See? All my code could be 100% correct, and I forget to do that. Nothing's written. It's pretty critical. And you can spend your time, you have a lot of code here debugging this when all you did was miss that. Okay, let's put it back and now trace through the file IO. It's actually fairly close to the input, at least is fairly close, I should say. Okay, the writing. The file writer, print writer. These are the two collaborator classes. This is the one that actually opens it for writing, data.txt. So even if I don't close it, of course it'll open it. It's going to be empty. It overwrites it. Now this is the higher level one where I can actually write strings, and we connect these two, file writer's class constructor. And now the one that does the actual writes, the print writer, println, and the paragraphs I entered are supposed to be written to file. They're not. They're written to the buffer right now. I omitted this, and let's ignore this for now. I omitted this. It's still seeing the buffer. It says that it should actually flush the buffer. In practice, every time with observations, it never does. So you better bloody well close it. Now, the alternative is the flush. The flush doesn't close the file, but as the name implies, it flushes the buffer. So there's a slight difference. Both of them flush the buffer. That's why I say alternative. If the learning lesson is to write to file, in that case, they're interchangeable. But this one does more than this one. This one removes the locks on the file. This one does not. Okay, so this is where we've written the file. Now the read, it's fairly similar to the scanner, but different classes. Open it. This is the one that's a lower level. This is the higher level one. Read line grabs the line of text. We store it in a string. And now the first line that we read, if the first line is null, this is where I got the empty file, nothing to read. Because, remember, none of that got written out of the buffer, folks. And now, line by line, if it's not empty, then line by line, the first line is echoed out, we read another line. And in this case, using the file reader and buffer reader, we're able to check for null as opposed to calling that method with the other classes with the scanner. Okay. Difference between scanner versus buffer reader, quick synopsis from Professor Hudson's notes. The scanner basically describes this. Okay, the scanner versus the buffer reader. Highlighting. The scanner reads a bit at a time as needed from the file. The buffer reader reads the whole bloody thing. Now he says technically it could be slower, but practically it's not, because with the programs that you write, and even existing ones, they're going to be small files if they're text files. You've got gigabytes of RAM. It's not going to have a noticeable difference reading in a few bytes. On the other hand, this one reads the whole thing. Theory is faster. Now this part here, he says why is it slower reading from disk? He says it's because it's further. It's not a hardware class, but since he again opened up that can of worms, we should be correct here and complete. He is correct where, okay, If we have something where the processor is here, RAM is here, there's a physical electrical wire that connects them. In order to communicate, we have to send electrical pulse. They're very fast, but the computer is operating in fractions of a billionth of a second. Time that it takes to go here to here is a time delay. So getting something from RAM is actually a bit of a time delay than getting something from a processor. The further away RAM is, the more distance it has to travel. The hard drive is further away still. So yes, it does add time, but it's not the only reason why reading from a drive is slower. I mean, if you think about its nature of the drive, think about the magnetic ones, physical movement, the spinning, the arm has to be able to find location. Physical movements is extremely slow. I just wanted to quickly add that because this is it leaves out some important things. Checking the configuration. So this is where we can use file checker, the file class, sorry, to be able to check. Before I just displayed the results, but here's where you can actually use it. File exists, it returns a Boolean. So what we're trying to do is this one just checks and it doesn't actually do any writing. But I'm just showing you how we can use the class files methods to do checks. If it's what we're going to do is we want to try and write to it if it doesn't exist. Let me think for a sec, can write to. If the file doesn't exist right here, then it's going to create a new file. On the other hand, if the file does exist, then we can write to it. Or potentially it's checking for, do we have permission to write? And all these conditions have to be met. The destination has to be a file because we can put in dot and no, it's not a file. We don't want to write to the directory. So we're doing the checks to prevent exceptions from occurring. One case where I tested this one, I will just show the screen grab to save time. Anywhere in the Windows drive, usually unless you set up user accounts, you can write. So it says can write to a file. But then I moved this to the C drive, and in newer Windows you can't write. You don't have permissions to create a file there. We don't have the ability to ask admin permission. So we got this one. Fine. Now we do the previous checks before we actually do the write. So we could use class file to do checks to prevent the exceptions. Recall I said it's better to prevent runtime errors than to handle it if you can. Some you can handle. So this code is the same as before. We check to see can we write and so on. The next code, given that we've done checks can we write, then we do the write only if, say, we have permissions to write. So if I ran it in the C drive directly, then this would be false and none of this code would execute. There's how we prevent an exception. On the other hand, if all the other conditions are met, we have the ability to write it is a file, then now we use a different class because he used buffered writer instead of the print writer, so I use buffered writer. The buffered writer, it writes strings. So in this case, it's an integer, converts it to a string. This is going to be converted. This is an ASCII code, 65, capital A. So it's going to write capital A. Non-strings converted to a string of length 1. And then it also writes a tab and false. So it's going to have capital A and false. If you run this program, you'll see the A and then a tab and a false. And then this part, I remind you, close after you write, otherwise it'd be empty. Why did I cover this? Because he covered it. Print writer is pretty much the common approach. Sure, buffered writer has some advantages, but not for this course. And this comes from his notes. He pretty much just says print writer, the one that is the commonly used ones, is more useful in terms of this course. So why did we talk about buffered writer? Because we had to, because he might quiz you on it. Okay, review. Good, we didn't fall behind. Now this part is necessary. Most of the concepts are the same. I have talked about system in, system out, system error. More though, the terminology. System in is getting keyboard input. But that's not the generic term, that's a Java specific term. Getting keyboard input, the term independent of language, this is Java specific, is a standard in. And you can look this term up. In Unix, Linux, they call it std in. But it's referring to the same thing. It's input that's coming from the keyboard, the user. In Java, they have they call it the system in, and they call it a file descriptor. It describes this is a file. We'll get to in a minute. Standard out, the file descriptor, the term is system out. It appears on screen unless you redirect it. I showed you that already in a previous example. Standard error does not get redirected. The file descriptor. Now these essentially are strings. We don't know lines in a file. So it's written as a string of characters or bytes or bits, depending on the level. Because they're coming in streams, streams can be coming from physical files or they can be coming from these ones. So these ones are referred to as file descriptors because these streams of input are also can be treated as physical files. That's why you actually saw scanner class. The stream can come from the standard in, but the stream can also come from a physical file. The standard in is basically treated, keyboard input is treated like a physical file. Other operating systems actually use numbers as the file descriptor, basically to classify which case applies. And you can actually check to see these codes, if you know what you're doing, which stream we're dealing with. Automatically, you start a Java program, it gets all three of these, even if we don't use them. This part over here, I will just briefly mention. To help out during reading week, assignment 2 was available. It was hidden, but instructors could see it. Permissions are set. So I looked at the PDF Professor Hudson had, and this doesn't match your assignment. I'll get to that in a minute. But I looked at it and I thought, oh, I used his notes as the core to see what's necessary. I found there were gaps. He didn't cover a lot of things like what the hell is it? Things like number format exceptions, illegal argument exceptions. So I created examples. Then assignment 2 was publicly available to you all at the end of reading week. Unfortunately, he pulled a switch. He didn't tell me that he's going to do this. I actually had to check to find out that he changed it. So this stuff doesn't apply anymore. I was actually going to provide this. I put this so you guys weren't shortchanged. I was actually going to let Professor Mahmoud know about this. It was already too late because this is already posted. So if it comes up later on in the course, the notes are there, but in case you wonder why it doesn't match assignment 2, because he swapped it out invisibly, silently. And I won't cover these for that reason. So next day, what I'm going to do is the only thing left in exceptions and files is this summary part, which explains what to do when you. I decided to add this extra one for this year. Since you have some time, I was actually behind schedule previously. When you call a method where an exception can be thrown, you actually have to include it in a try block. That's what you've seen so far. However, there's alternative approaches as well too. You've seen some of these. This is kind of a recap of some of what you've seen, some of newer things. The one that you've seen already, if we're calling this method, and you can see over here that the parsint, there's a possibility that it's going to throw a number format exception if we can't convert it to an integer. And then throw, of course, means that it's going to not only instantiate an instance of a number format object, but then execution transfers to the corresponding catch block that you've seen not only in this course, but also in previous course with the Python exception handling model. Method 2, what we can also do is say we're going to call parsint. Parsint again still can throw that number format exception. If we can't handle it here, seen previously, where the calling method can't handle it, then the calling method, now this is the way of handling it. We handle it by having a catch block one way. Another way is we don't have a try catch block, but the method that calls parsint that can throw an exception in turn throws an exception. So it doesn't handle it. It takes this exception object that gets transferred back, and this one doesn't deal with it. Instead, it goes back to its caller, and that caller has to handle it, or eventually it goes back to main. Method number 3. So if the unchecked exception in this case, where we've got scanner and we don't actually have to check it, what we can do is potentially we can throw we have an IO exception general one, and we could throw a new instance of a different type of exception here. So yes, we have that try block, but we're getting more specific. Rather than just an IO exception, we actually create the right type of exception, the unchecked IO exception. And what I've done is I'm calling the constructor. So this throw, there's a difference. This is an action. It's performing an action and transferring, it's creating an object, and then it's transferring execution, throwing it back to the catch block. Well, over here, what we have is this is throw, plural, singular instead of plural, and this is instantiating, get rid of that throw part, a new unchecked exception, and it will throw it back to its caller, whoever called this method here. This one, plural, does two things. It creates an object and transfers back. This one transfers it back to the caller. Now we can have over here, I create another example, the driver how to handle the exceptions. So we've got method one, where we've got that formatting, in case you wonder. Yes, I do format things, but even though I use consistent with spaces, sometimes IntelliJ gets a little wonky. And are these ones all, oh, this one's all consistent because I reformatted it again. If you see my examples, it looks funny in IntelliJ. It's not that I didn't format it. It takes the 4 spaces that I consistently use, sometimes munges it. Okay, so the classic way over here is method one, you'll see. And we call the parseInt. We pass to it something that can't be converted to an integer. So execution is going to transfer here. I can run it again. We see the result of it, but I'll show this dynamically. Okay, so it ended. And where's the annotations? The annotation, the freehand. So this one, method one with this approach, we see that message appear, and we also see that final example. Now, the exception occurs in parseInt, and we transfer, then execution goes to here, because this is where we're calling it. This is the corresponding catch block. And what it's doing is, see that string we passed to parseInt, it's saying for this string, we can't parse it. Okay, that's the first approach. Now to clear this stuff and get out of annotate mode. Method number 2, that's where we call that method in the try block. Let's see. And we call calling method. So calling method itself throws the exception. You see what we're doing? The reason why this is in a try block is when we go from here, see if I can have both of them and pull it down a bit. I can annotate. Calling this method, and I made it, I don't like doing the non-all approach, but you have seen static in this course. And if I had another class, another object, I have to be jumping between class definitions. So since you've learned static, I've done it this way, not OO style, but for simplicity. So calling method itself, because it throws a number format exception, when we call calling method, it has to be enclosed in a try block. And potentially it can throw that action throws, so it's plural here, potentially, but it hasn't done it. And now we call parseInt. When we call parseInt, no try. Remember, that's the second approach. Second approach is when we call that method, the original method that can throw an exception, we normally have to have that, or is it right here, put it in a try. There's no try here, but as a replacement, the method that calls parseInt throws an exception, and then execution will transfer down to here, and I pass to it something a little bit different. Method 2, 123.1. Method 2, that message appears. Method 2, 123.1. Oh, here's the method 2. The method 2, I had it where we're calling it somewhere right here. That one appeared. That's we had that one appear. And then we have method 2 we pass to parseInt. Method 2, 123.1. That, of course, is going to produce an exception. So execution transfers here. It can't handle it. This throws it back to its call over here. So that's method 2. Method 3, these are review. The third one's different. So you get method 3, the message method 3 appearing. That's not a big deal. We have a string 123.1, and we pass to parseInt. Well, this over here cannot be an integer, and parseInt strictly has to take all digits that are whole numbers. And this is not, so it doesn't do anything like truncation or rounding. It just throws an exception. Fine, we have to call the parseInt that's going as a try, but what we can do is go from the number format, the general one, to creating a number format exception over here. Again, it looks a little bit funny. We've got number format exception here. We have number format exception here. But rather than having these generic messages over here, what we can do is we pass constructor our own custom message. Method 3, 123 is not an integer. And see, we have this message I passed the constructor, a custom message. And it's not a real program, so it's not as useful as it seems. But the point is, whatever might be useful to help someone debug it, we can have a custom message. And what I had previously in that other version actually didn't have this as a complete example. I said right back at you, which obviously doesn't sound like something that they code up as a generic message with Oracle Sun. So this shows the 3 methods, and in this way where you can actually create a new object with your own custom message that might be a little bit in a real project, not a toy program like this, where it might be more useful for someone who's using your code to debug this. So